Good morning, everyone, or good afternoon. We are going to start momentarily or just waiting for everyone to join. All right, we are going to begin now.
Hello, everyone. Welcome to our seminar, Where Should the Metals for the Green Transition Come From? It's my pleasure to be your host. Many of you I know, and those that I don't, I look forward to meeting one day. My name is Greg Stone, an oceanographer, and currently the Chief Ocean Scientist for Deep Green. Throughout my career, I've tried to find ways for the ocean and people to both thrive and support each other in the modern age, an age when one species, ours, has colonized the entire planet, and our actions must now be managed at the planetary scale. I love the ocean, as I'm sure most of you do, and I've done over 10,000 dives using scuba, submarines, and underwater robotics. I started my career in basic research, but when I saw firsthand the decline in ocean health in the early 90s, I changed and devoted my work and life to conservation. I've written 4 books, dozens of scientific papers, edited a science journal, and led expeditions for National Geographic about diving into icebergs, coral reefs, and even living underwater for weeks at a time. Prior to Deep Green, I was Chief Ocean Scientist and Executive Vice President for Conservation International, chaired the World Economic Forum's Ocean Council, and co-founded the Ocean Health Index. Along with spending a lot of time underwater, I was privileged to be deeply involved with the country of Kiribati when they created the Phoenix Islands Protected Area, the first large-scale open ocean marine protected area. It's about the size of California. But I joined Deep Green because I wanted to help the world meet the upcoming demand for certain battery metals required for our renewable energy future with the lightest environmental impact possible. Today, you will now learn the results of a study conducted on the comparative impacts to the Earth from acquiring these metals from traditional terrestrial mining and the special case of polymetallic nodules. At first, it may seem counterintuitive for an oceanographer like me to be involved with this, but learn with me from our 2 speakers how humanity must look at this issue from a planetary scale and the trade-offs from these 2 very different sources of metal, especially and importantly right now with the urgent threat of a rapidly changing climate. Now I'd like to hand this over to the lead authors of the study. Thank you.
Thank you, Greg. So my name is Allison, and if you have any questions during the webinar, we invite you to submit your questions via the Q&A feature shown at the bottom of your screen. I will be moderating the Q&A portion at the end, and we will be answering your questions that are both asked throughout the presentation as well as questions that were asked in advance. And we will do our best to answer all of your questions, but if we don't get to all of them, we will be following up with a complete summary of all the questions and their corresponding answers in the coming days. So Deep Green commissioned this study, and independent consultants, Dinah Polikas and Dr. Steve Katona, led the development of the white paper, and they will be leading this webinar today. So Dinah and Stephen, please introduce yourselves.
Thank you very much, Allison, and thank you, Greg, for the kind introductions. And I hope everybody's doing well at home in these strange times. Thanks for tuning in. I'll briefly introduce Stephen first, he has just been an absolute delight to work with. He is a marine ecologist with a treasure trove of knowledge about all aspects of biodiversity and sustainability. He's another co-founder of the Ocean Health Index in addition to Greg. And he's also on the board of the Marine Conservation Action Fund. Very impressive background, undergraduate and PhD in biology from Harvard, Fulbright scholar. He was president of College of the Atlantic for 18 years, as well as a founding professor there. So he is going to spend a lot of time providing detail about the biodiversity and other environmental impacts results from the study in the second half. Steve, you're muted.
Great. Thank you, Dinah. And it's a great pleasure to introduce to you Dinah Polikas. She's an industrial systems engineer. She trained in physics at Caltech, got her master's in business administration at Harvard Business School, and then a master's in econometrics and mathematical economics at London School of Economics. So she's an independent consultant, as am I, and she chooses to work on complex global problems that are really urgent, and she works to identify and understand paths that can help solve those problems. The problem that we're discussing today certainly qualifies, and she's been an absolute workhorse on this project from its very inception. Her energy and expertise and her extraordinary work ethic have powered this thing through, and I'm very proud to introduce her and to ask her to begin the webinar by sharing her results for the first portion of the presentation.
Thanks for that, Steve. So both Stephen and I were very motivated to understand the full picture behind mining nodules to solve a particular global problem, which I will soon be explaining. And this decision really does have global implications, and that's what we're going to talk about today. But first, I just want to call out a couple other people involved in this effort, just very important to note. It wasn't just me and Steve working on this for a year. We had a great team of 5. Greg Stone, our host, a globally known marine science and conservationist, as you know, and he launched the first version of this study, and he's helped frame the questions we'll be addressing today. Erica Ilves, who provided enormous strategic, systemic, and quantitative skills in making contributions to this work, and also Tony O'Sullivan's decades of experience in the mining industry that really grounded our inquiry in ways we couldn't have done ourselves. These are deep green folks, and furthermore, we leveraged numerous experts, including the one shown here, for instance, to validate some of the study approach and methodology and deep dive some of our analyses. So it was a tremendous group effort. Before I get into the structure of the talk, I just wanted to point out 4 things I hope you'll take away from this webinar, if anything, to remember. The first is just big picture drivers of impact. Just what causes the negative environmental impacts of metal mining and metal production today to begin with. Just an intuition about that. A second is a sense of how nodule impacts overall compare to land or mining impacts across the pillars of sustainability. 3, we want you to have a sense of what biodiversity does live in the deep seabed, and also how this compares to the landors. Also what we do know and what we don't know about the ecosystems we're affecting, and what we're trying to find out in the coming days. And last, 4th, a global big picture view beyond environmental. What are the important social and economic implications of nodule mining compared to landors? So with that, here's how we'll approach today, roughly split into 3 parts. I'll start with the big picture study motivation, structure, and methods, summarize the difference between the 2 middle sources to give you a bit of a sense of why to expect impacts to be different. Talk about the climate change results. So there are 5 sections of results, and I'll then go through the first, the climate change, and the second, economic impact differences. Then I'll hand it over to Steve, and he'll finish off with an overview of the non-living resources impacted by producing metals from these 2 sources. Then he'll explain in detail the biodiversity you'd see in the different habitats. And then I'll go into the social impact from producing the metals. And finally, he'll summarize for you the big picture, the results of the entire paper. Then we'll enter into the Q&A, and again, please feel free to enter questions, and anything we don't get to in the 25 minutes, we will certainly follow up afterwards and continue the discussion. So I'll begin with the study motivation and structure. And so the question is, why is mining even an issue today? And why is this even a problem to consider? So that are motivating us to even address this nodules. And there are 4 parts to consider in this puzzle. First, the market projections. So there's a lot of demand coming as part of the global green transition to renewables. And we juxtapose this secondly against the climate crisis, which the urgent need to minimize carbon emissions as much as possible, as soon as possible in order to meet targets. Third, you have tremendous environmental and social impacts with mining today as it's done. And so if you scale up the current impacts to meet that coming demand, you're hitting up against problem number 2. And furthermore, it's not just the climate change impacts, it goes far beyond, including habitat damage, waste, toxicity, pollution, tailings dams that collapse or get toxic, threats to biodiversity, and many others. We'll be discussing all of that. Last of the 2 of the 4 metals we'll be talking about today, cobalt and nickel have complexities in their supply chain that make it difficult to meet that coming demand. For cobalt, it's partly very low ore grades, as well as a substantial amount of unsafe artisanal mining and child labor, a concentration of the mining in the DRC, 60 to 70% coming from there. So geopolitical issues and supply chain concentration, which is risk. For nickel, it's a mismatch of resource types ideally needed to produce battery-grade nickel sulfate, along with declining ore grades as well, which worsen the impacts. So set against that problem, these all issues on the slide have to do with some sort of sustainability impacts or sustainability being problematic. And I'm going to first dig deeper onto the green transition and focus on electrification of the global fleet. So I want to show you this chart from Morgan Stanley 2017. The blue curve on top is normal internal combustion engine vehicles. The green curve on the bottom is fully electric, battery electric vehicles, where they cross in 2047. In this projection, you now have 1 billion EVs operating globally. And that's just passenger fleet. So this curve is showing exponential demand growth in EVs. And why does that matter? If you're talking about things at this scale, well, it matters because one big piece of sustainability is the life cycle emissions impact, and that's going to also scale. Or the carbon dioxide equivalent life cycle emissions of producing and operating an EV. So this chart shows you the life cycle emissions impact on the left for a regular car, an average, for example, an average European car, internal combustion vehicle, ICE. And on the right, you have a Tesla Model 3 as an example of an EV. Various bars because each bar represents a different country where the vehicle is being operated. So if you notice Norway in the rightmost bar, it has, since Norway, the country has a renewable electricity grid, it means there's no impact from the recharge aggregating into this total life cycle emissions. So there's no green in that bar. So that's kind of a best case. If you compare that best case all the way to the left bar, it's about a 50% reduction. So even in this best case, you still have a substantial life cycle impact of emissions. And why? Most of that's from the teal part, which is the battery manufacturer. So you see that that makes up an enormous amount of an EV's life cycle emissions. And most of the teal bar is from the metals inside the battery. And so if you make metals for 1 billion EVs, then that has a huge emissions implication. And that's definitely a problem worth looking at. And so how much metal exactly? So if you start with a single battery, this is the battery used by the Tesla Model 3. It's called an NMC 811, which stands for nickel, manganese, cobalt, and 811 is the ratio of the metal of those 3 metals in the battery. And incidentally, the metals used in this battery, plus the copper for connectors and harnesses, are the same 4 metals in the CCZ polymetallic nodules that we're interested in, that we're studying. And so one EV, one Tesla Model 3, requires this quantity of metal, 155 kilograms total. And so if you have 1 billion of these as a standard and multiply by 1 billion, this is what you're seeing in terms of 155 million tons just for the electrification part of the global vehicle passenger fleet for the overall green transition. And that's just part of the green transition. So here, when you consider all of the green transition, like shifting to zero carbon power and electrifying industrial processes, you start to see numbers even bigger. And note that transportation alone makes up to 14% of global emissions. In the US, it's 19%, so reducing this can have a substantial impact. And so there's urgency to revamp these things quickly, given the remaining climate budget. And so the urgency in tackling this metal resource question comes now as a result. So given that you accept we need this new influx of metals, and there have been questions on this, which we're happy to talk about during the Q&A, but the question is now, where should they come from? Where can we get them from? So recycling is the first one that we would love to say is the answer. Unfortunately, right now, there's not nearly enough metal stock to supply that new demand with recycling. There was just a World Bank report that came out that revalidated this and ran scenarios of these same metals for the same green transition and showing there's a huge deficit. So it's not a near-term option, unfortunately. So the options are either ramping up land mining to meet the new demand or meeting it with a different source. So if you look at the ocean for the different source, of the 3 places there that have lots of metals, the ones listed here, note we're only focusing on the polymetallic nodules. So the main reason is the other 2 are more invasive to mine, which means likely more sustainability impact. And also the nodules are of great recent interest with exploitation leases currently under consideration by the International Seabed Authority. In fact, the ISA has regulatory decisions set to be taken in the near future. So this is very imminent decision and information to be thinking about. And just so everyone is familiar with what nodule collection may look like, in case you aren't, they're collected on the sea bottom by a collector machine. Typically be pumped by some sort of riser pipe up to a ship. There's some water that goes up with the nodules to the top, would get strained out, pumped back down to a certain depth. Stephen will tell you a little bit more about that likely. And those nodules then at the top are loaded onto another ship, which can be shipped anywhere to whatever processing plant is the desired location. So in the study, taking that, we are comparing the impact from using nodules versus current practices of extracting metals from land ores, specifically saying, in source one, what would the world look like if we don't embark on this at all? And source two, what will the world look like if we do? Specifically, to use that source for the metal demand to electrify the passenger fleet with the 1 billion EV scenario, and then we compare the impacts. And so what impacts are we assessing? Very quickly, so we framed this by looking at all the sustainability pillars. That's environmental, social, and economic impacts. Everything we looked at ties into one of these pillars. We prioritized based on relevance, and each individual impact was assessed using a tailored method, which is detailed in the paper, the combination of qualitative and quantitative techniques, grouped into a number of categories to help summarize the results, and we will go into some detail on each of these topics. The underlying basis for much of the analysis was a standard called Lifecycle Assessment, or LCA. The LCA is an ISO standard analysis framework for environmental trade-offs, and originally, but expanded to then also include in economic and sustainability. And it's for comparing impacts of multiple options. There's extensive LCA literature pre-existing for metal production using land ores, and we leverage those results. And a key concept I'm showing in this graph here is cradle to grave versus cradle to gate. So cradle to grave considers the full life cycle of a product, as you'd think. This is like the bars that I showed before. So for an EV, that would be mining the ore, manufacture, using and charging the EV, maintenance, disposal. It also includes indirect material and energy contributions all along the way. And both cradle to grave and cradle to gate include all those indirect contributions. What's of interest to us, though, is the second concept, cradle to gate, which is the standard way to compare impacts of producing a material, like a metal, or a commodity, where once you have that in your hand, it doesn't matter where it came from, you can use it in various applications. So that includes mining the ore, processing, refining the metal, and it stops before the manufacture. And that's what we use, that's the standard, and that's what lets us compare the impacts of making 1 kilogram of nickel sulfate from an Indonesian laterite mine versus 1 kilogram from the CCZ nodules. And so to do that, on the left, you start with the cradle sources, whether land ores or nodules. On the right, you have the nickel sulfate, cobalt sulfate, copper cathode, manganese sulfate. Then you have 3 stages of metal production around the top that are common at an abstract level: mining, processing, and refining. For land ores, we then use literature review to identify studies and best sources to represent an average baseline of impacts for making each one of those battery metals. That's all coming from existing sources. For nodules, there's not yet a commercial production system, of course, so we created a nodules LCA model. We used standard ISO processes, databases, and tools to do so, a number of inputs, detailed metallurgy flow sheets, independently compiled, Canadian standard compliant preliminary economic assessment, which is important because it meets a high level of rigor, and it was independently compiled and has a wealth of data that includes the information one would need to create an LCA. And all of this was based on the proposed assumptions behind proposed deep green system. We can talk a little bit more about the assumptions that go into this, and you'll see later in the presentation some of those details. And together these contain the key information and material and energy flows and outputs necessary to compute an LCA. In reality, there's quite a variety of models and computations that were undertaken over the course of 12 months. And so again, we use prioritization and tailored methods based on the questions being asked. Here you see a list of indicators used and detailed assumptions found. And each of the 5 impact categories has a dedicated results section, and more background than what I just presented is available. Short talk, can't get into all of it, but you can see several introductory chapters if you want any more information on that. So now I'll give you a very quick view of the key differences in metal production from land ores and nodules to give some sense of why nodules should have a lower sustainability impact, as we see. There are 3 main categories of differences that will affect the impacts: the ore locations and natural surroundings, the characteristics of the actual ore, and the methods by which the ore is processed. So first, the geographies disturbed by land mining are very different from nodule geographies. So on land, here you just see the top producing countries of the 4 metals for each of the 4 metals using land ores. Notably, they're found in geographically diverse areas, and many of them in areas very rich with biodiversity. If land ores are mined from areas rich with biodiversity, that means clearing forest, disturbing animal habitats, and often causing pollution for the communities. And so that's some of the drivers. In contrast, nodules and other ocean resources are obviously located in the ocean, far away from human communities, lower densities of creatures. And in the CCZ in particular, is even far away from fishing communities. The CCZ, the area of interest is there, circled just above the Pacific Ocean, so the Clarion-Clipperton Zone. This map shows all three types of ocean resources. The nodules are in blue. The yellow indicates seamound areas which have thick sulfide crusts that also have lots of metal. The red lines are hydrothermal vents, which also have lots of metal. And these are the areas people have considered mining. But as I mentioned, this study doesn't consider them. It only focuses on nodules, and specifically the resource that we have documented in the CCZ. And here you see that close up, color-coded are the lease areas associated with different contractors. And also in bright green boxes, you can see the protected areas of particular environmental impact, APEI. If you look closely, only about 27% of the CCZ floor right now is contracted for exploration, and over half of it is set-asides that won't be touched. It's vast resource in terms of size, and it has enough metals to electrify the global fleet several times over, in fact. But relative to the entire world, it's only about 1.5% of the total abyssal plain area, and only about 2.5% of the total water volume of the Pacific Ocean is the waters overlying the CCZ. If you take a closer look at the land ecosystems, these areas can be very rich in life, from Indonesian rainforests to wildflowers blooming in the desert. We'll talk a little bit more about these later. In contrast, the physical environment of nodule ecosystems is fairly stark, partly due to the extreme depth, 4 to 6 kilometers deep, intense pressures and lack of light reaching it. It means nodule areas are very food poor, and so few creatures live there as a result, and the ones that do tend to be very small. Stephen will later talk about types of organisms living there and the potential ecosystem impacts. Evidently, the fewer quantity of animals, let alone human community, remoteness, you might think should have a smaller harm in comparison to land mining according to those types of metrics, and we'll see if that plays out or not. The second main difference has to do with the ore itself, the ore characteristics or mineralogy. On land, the grades for nickel, copper, and cobalt are low, and nickel and copper grades have been declining and continue to decrease. The reason this matters is if half of the ore grade means twice the ore that needs to be dug up and processed, which means much higher LC impacts and also means more waste produced. And so you see waste as two main categories: overburden and waste rock from the actual mining process, and then processing waste, which includes what's called the tailings, which I mentioned earlier, which can be toxic, have to be dammed up, they have to be managed indefinitely, they can be mismanaged, there can be tailings dam collapses, they can become toxic and harm communities. Nodules have two key differences in this respect. First, the actual grades are higher, there's constant, they're not degrading, they're well documented and known in the CCZ. Copper and cobalt from nodules both have more than twice the average ore grades versus the land ore average. And so high and constant ore grades means less waste. And the other key factor is the lack of heavy elements in nodules, so only trace amounts are found, which means not having to worry about managing large amounts of toxic waste, and enables contractors to produce zero waste processing design if they choose. And then the third difference is in how they're processed. So I'll just show you this one diagram. And the key things to notice, both land ores and nodules, again, have roughly similar looking 3 phases, but the details are where you'll see key advantages and disadvantages. So processing land ores has some handicaps with coal-intensive reduction if ores are oxidized, which is common to both. Lower ore grades, means more effort to extract, also means concentration or beneficiation, which has a high footprint. Trucks have greater impact per ton kilometer versus ships, and you're constrained in using local electricity grids, which often means higher fossil content on average and more impact. In contrast, processing nodules gets, you have the flexibility of using ships to take the nodules from the resource location to the processing plant, and they're less polluting on average, and also give you location flexibility of where to place that plant. And also collection is less invasive. There's no drilling, they're sitting there on the surface to be collected on the seafloor surface. There's also 3 potential advantages based on choices of contractors and accessible to all contractors. One is the use of hydropower or renewables, because you can ship the nodules anywhere to any coast. You have a lot of choice in site selection for those plants. Another is flow sheet design choices and eliminating wastes and residues that can lead to zero waste design. So, results. We'll start with the climate change category. So this analysis consisted of 2 parts. I'll start with the life cycle emissions, which is with the full LCA analysis. And for emissions, we did this, the full cradle-to-gate study. We figured out the per kilogram impacts, extrapolated them to a billion EV scenario. And for landors, we also applied an aggressive green scenario if fossil electricity were phased out by 2050. And the result of that is shown here. So shown against an image of a polluting Norilsk smelter, Norilsk, Russia smelter, you see about 1.5 gigatons of carbon dioxide would be emitted using landors to make just the metals for 1 billion EVs. And again, this is the number for the green case. And comparing this to global emissions, that's about roughly 37 billion tons emitted per year. This is a large number contributing to that if you're considering that the only thing we're looking at is just making metals for vehicles in the next couple of decades. Also note that the IPCC budget here is, as of 2018, is for a 66% chance of staying within 1.5 degrees Celsius. So this is the 1.5 degrees budget. So let's compare that. And you see that for nodules, you see just under 0.5 gigaton, so more than 2/3 less emissions. And so usually using nodules to make 1 billion EVs saves a full gigaton of emissions out of our remaining budget. And if we want to see these results on an individual metal basis, this chart shows per kilogram global warming potential for each metal, comparing landors to nodules, the base case without the green adjustments. And you can see emissions reduction varying from 22% up to 80%, depending on the metal. Also, you can compare the total scenarios, the baseline land case versus the green case. And so even these electricity grid improvements can lower emissions substantially. So from 1.85 to 1.5, but still you get a far bigger reduction if you go all the way to the nodules. And the colors there correspond to the metal. So that big light blue chunk on top is the nickel contribution, which is the biggest. And then the next biggest would be the copper contribution on the bottom. So I'll quickly turn now to the carbon sequestration impact. So just to define this for everybody, it's the long-term storage of carbon away from the atmosphere or air for decades, centuries, or longer. And on land, sequestered carbon is found in vegetation and soils. In the sea, it's found in the seabed sediments, as well as in the seawater itself as dissolved inorganic carbon. And there's been speculation that nodule collection might impact carbon sequestration. So we looked into these mechanisms. The first type of impact, generally speaking, is the release of carbon that's already been sequestered. So on land, if you cut down trees and vegetation, bacteria will oxidize the organic carbon and release CO2 into the atmosphere. For nodules, there's actually 3 ways it might be released. One is that nodule collection will stir up some sediments, and some carbon theoretically could rise to the surface, so we quantified this. Second, some seawater is brought to the surface along with nodules, and so some dissolved inorganic carbon might escape. Remember the riser part, so that seawater, while it's shortly at the top, might theoretically have some dissolved carbon escape. And then last, the nodule collection does have a land footprint because vegetation is cleared for processing plants, and there are indirect impacts from making the metals that made the ship that's used for the collection. So those are all considered in this analysis. And the second method of impact is carbon that otherwise would have been sequestered in the future, but does not get sequestered because services have been disrupted for some time. For example, on land, the mine is there, you no longer have the trees and vegetation pulling the carbon out of the atmosphere. And this continues until the land is reclaimed and trees have regrown. In the sea, the bacteria responsible for sequestering carbon may be displaced, may be removed along with the nodules, and that continues, that disruption continues until the bacteria regrow. So we looked at both of these in turn for landors and nodules. And here's the results. For landors, this is the amount at risk using landors if care is not taken to prevent its release. So compared to the previous number, that's even bigger, 9.3 gigatons of CO2 at risk. And then taking 100 years, since a mine is typically in operation for decades, and then it takes decades or more for land to be restored and trees to regrow and fully restore the function. We considered a conservative scenario of 100 years, use the same scenario for the nodules, during which the affected land we assume does not sequester carbon at all. And this is the number that you see from there. Now we compare that to the nodules, and right away we see that despite concerns we've heard, there's far less sequestered carbon at risk with the nodules with all these 3 mechanisms combined in that number, the 0.58. And in fact, most of that 0.58, if you decompose it, is due to the onshore physical processing plant footprint and the indirect impacts. So the actual sea contribution using the mechanisms we went over is very, very small. And then comparing the same 100-year scenario of future carbon not sequestered, similarly, we see a drastically lower number with nodules. And again, most of that is from its land footprint. And so for the climate change impact in both life cycle emissions and carbon sequestration analyses, you see huge reduction of impacts by using nodules. In total, up to 11 gigatons CO2 might be saved. Now, when you compare that to the budget, that is substantial dent and worth, again, noting. So finally, I will jump into a brief discussion on economic impact, as I believe I'm a couple minutes behind, but I will go quickly. And so broadly speaking, there are 4 parts of economic impact to consider that are relevant, and I'll touch on at a very high level. So 1 is production costs, 2 is jobs creation, 3 is impact to individual countries, and 4 is economic risk or global systemic risks. So the first one, production cost, you can gain insight by looking at what's called a cost curve. And this type of graph stacks producers left to right according to their costs. So the highest cost producers on the right. Metal price tends to settle around the 90th percentile costs, shown here as a red line. So producers at the right of the curve may need to innovate or alter operations, or they may be at risk of being pushed out of the market. Producers at the left are lowest cost and have an advantage. They have a healthy margin. Here, this is specifically nickel sulfate cost curve projected at 2025. And we see based on the preliminary economic analysis that nodules have a significant cost advantage predicted. Second, to look at jobs. One way to examine this for the landowners is just projecting today's per country production percentages to the year 2047 and apply that to the new metal demand for EVs in that year. So this chart can be taken as new jobs created by the green transition for EV batteries in the absence of nodules. And it shows it by country from left to right. So it's net new jobs if nodule collection is not started. The line is the number of jobs, and the circle size indicates the metal tons produced by each country. The colors indicate which metal. And so you can see which countries might be contributing metals to build EV batteries and getting jobs absent nodules. We separately also modeled nodules. It's interesting geographically because the jobs and metal tonnage aren't predetermined. The countries receiving them aren't predetermined because it's an international asset. So 3rd and 4th economic impact topics were about individual economies as well as global and systemic risk. So one way to look at this is just to consider how individual metal markets look and who are the players in those markets. So the 4 graphs here show the dot in the middle are the projected year 2035 global market of that commodity. The shaded area is the demand specifically for EV metals. And so you see almost all of the demand for nickel sulfate in year 25 would be for these battery metals and for battery metals. For cobalt sulfate, it's a substantial portion. For manganese and copper, it's a much smaller amount. So this is one illustration for why market analysts are saying there's a massive supply gap coming because the exponential increase for nickel sulfate and cobalt sulfate are going to disrupt their markets. We're starting with very low levels currently. Copper may be fairly unaffected. It's larger, more commoditized and diversified, although you still see a significant amount being contributed by the EVs. And then manganese has a slightly different story, which I'll finish with 2 quick pictures on that. Here, this chart shows how much of the 4 metals might be produced in the year 2035 again. This would be along the path to 1 billion EVs using nodules. So the top row is the output from nodules. The bottom row is demand for EVs of each of the same metals. So supply and demand, you can see are pretty well matched for 3 of the 4 metals, but for manganese, because the preponderance of manganese in the nodules, if we mine enough metals to make the EVs using them, there'd be some possibly excess manganese on the market. So if you ask yourself, what does that do geopolitically? To think about this, I go back to the cost curve for manganese, and I look at where the country producers sit on the cost curve. So here you see China in blue, you see Gabon in orange, Ghana in red, South Africa in green, and then other countries are in gray. So the guys with the greatest risk are at the right side. This is as of 2018. It's actually a few of those Chinese producers have already dropped off on the far right. Most of the African countries seem to be fairly fine if they're middle or below median, below or around median as they seem to be in this chart. And so it's very difficult to predict how the market will evolve. Manganese is also used in steel and other elements of green transition. But broadly speaking, this kind of chart helps give you a sense of who might be at risk and who might not be. And so to quickly summarize, stacking up all the economic results, here's what we calculate for 1 billion EVs using land ores. And then you see nodules are much lower cost. They create fewer but safer jobs. They tend to be higher tech, no artisanal jobs. And then many national economy benefits, including that sponsoring states and recipients of ISA funds, which are set aside royalty amounts to help countries that may be impacted by any of the economic impacts of the mining. There's a fund for that, which is substantial, and it's not constrained by geography. And at the same time, providing global stabilizing force for the nickel and cobalt sulfate markets. There, now, so I hand it over to Stephen for his half.
Hi, everyone. And now we'll start looking at the effects on non-living resources, and then following on to that, the living resources. Things get interesting. So we looked at non-living resources impacted by metal production. We looked at wastes, the amount of ore extracted, the amount of land used, amount of forests cleared, water use, toxins, and eutrophication chemicals released, and also cumulative energy demand of the processes in both cases. We're always looking in terms of the production of the 4 metals for 1 billion batteries. So the numbers Dinah has presented, and we're now going to look at the results in order. First, we'll talk about waste. As Dinah mentioned, ores on land are typically covered with overburden, it's called. That's the overlying rocks and soil that has to be removed to get the ore-containing rocks. And the proportion of the metals in ores has been falling steadily as the richest sources have been exploited already. So what we've found is that to make 1 billion batteries, about 64 billion tons of waste will have to be produced. Mining is very productive of solid waste. It's rocks mainly, as well as processing wastes, about 350 gigatons per year. And that's about enough to cover the island of Ireland to 2 meters. That's a lot of rock. It's not just innocent rock. As it is exposed to rain and bacteria, it sheds toxins and acid, and that is harmful to land and water. We'll get to that. Because the ores in nodules are much more concentrated than on land, and there's no overburden, you can get the same amount of metals by only mining or collecting 25% of the amount of mass. Mining on land uses quite a bit of area, all told, for not just obtaining the ores, but also for making the machines that are used to harvest them, and also for producing the refineries and factories and roads and everything else. The production of 1 billion tons, 1 billion batteries would use about 156,000 square kilometers, slightly smaller than the area of Tunisia. In comparison, nodules use a lot more space, 508,000 square kilometers of bottom in the CCZ. Nodule production also uses some land, shown in the top thin green line, about 9,800 kilometers for refineries, and also for the ores that went into making the ships and other equipment needed to get the nodules. So in comparison, mining nodules takes a lot more seafloor. I should mention that land ore production not only uses 156,000 square kilometers of land, but it also uses several thousand square kilometers of ocean for the placement of deep sea tailings in countries like Indonesia and the Philippines. So the contrast is not just in the size of the areas used, but also in the type of life present. There is no plant life on the bottom of the ocean. 12 times fewer organisms, no competing human uses. Carbon sinks are not disturbed as far as our analysis goes. Species extinction risk is present, just as it is on land. Along with that, or I should say included in the 156,000 square kilometers, is about 66,000 square kilometers of forest that are cut in order to make the 1 billion batteries. That's about the same area as Sri Lanka. Much of it is tropical forest, but not all. The mines for these metals on land are distributed really quite broadly, but the main producers are in high biodiversity areas. Mines are pretty thirsty for water. Land mines use about 45 gigatons. That's about 45 cubic kilometers of water per year. That water draws down groundwater resources, lakes, streams, rivers, and is a problem for wildlife as well as for human communities. To make the 1 billion batteries, about 11 years worth of average global water consumption would be used. And that amount of water would cover the entire island of Jamaica to a depth of about 4 meters. Also, the land ores, as I mentioned, the rocks that are stored on site, and the processing wastes that are stored in tailing dams are toxic. And here's something that's a little bit complicated. About 24 metals and compounds are toxic, and each one of them is not analyzed for its own particular toxicity, but it is in the LCA framework, which is used globally, it is compared to a standard toxin. The standard toxin used is 1,4-dichlorobenzene, which is actually mothballs. It's a pesticide. And so the danger of the amount of toxins released is expressed in terms of the amount of dichlorobenzene that would have the same toxic effect. So the amount of toxin on land, this is for pollution of land, is about 33 million tons released. More goes into water because the acid mine waste and its contained metals flow into lakes and streams and also percolate down into groundwater. And that represents about 21 billion tons of freshwater ecotoxicity expressed in terms of toxicity of mothballs. It's about 4 Lake Michigans worth of toxin. But some of the released compounds or metals are not toxic. Some are fertilizers, and they're expressed in terms of the amounts of phosphate that would be equivalent. And that is flowing into streams and lakes and also into the ocean. And that's about 80 million tons of phosphate equivalent that is produced during the land sourcing of metals for 1 billion batteries. All of this is energy intensive. About 24.5 petajoules of energy are consumed. Now, this is not just electric energy, even though an electric substation is shown here. It also includes any fossil fuels used in the process, coal, anything else. And so for land ores, the whole process of making 1 billion batteries would take about as much energy as would power 95,000 homes for 10 years. So we're going to compare land on the left and nodules on the right. There are the numbers, and you'll see that in every case, except for the amount of seabed use, nodules are much less impactful. The only small additional case where nodules use a little more is in the cumulative energy demand. And this is because the nodules use coal as a reductant, It's not burned, but it is used as a reductant in processing. And it may be possible to find a substitute in the future, but in any case, they're about equivalent now. Let's go now to the part that so many of us are interested in, the biodiversity compared on land and in the water. The basic problem we have is that the types of organisms that live on land and in the water are very, very different. Here you see some examples of animals that are threatened by mining. A glass frog recently discovered from Ecuador, salmon in the Bristol River watershed, one of the world's largest bats threatened in Philippines. And here, some of the sea cucumbers, serpent star on the bottom. So we're dealing with really two different sets of animals, both in size, in complexity. These are mostly vertebrates. These are invertebrates. They're beautiful, don't get me wrong, but it's very hard to compare these things, and that's what we're going to look at here. In the middle, all this stuff is a schema that is universally used for life cycle analysis, and it's got stages and steps and all kinds of complexities that Dinah has dealt with. The problem is that it can be used to look at damage to species and biodiversity, but it is not a satisfactory way of doing it for the kinds of problems we're facing. So what you have are choices. You could quantify the number of individual organisms at risk. We did that. You could quantify the number of species at risk. The problem there is we don't know all the species yet, certainly in the deep sea and even on land. New ones are expected to be and are being discovered. You could categorize them by size and biomass and so forth, or by the number of endemic and endangered species. And you can also look at the ecosystems and compare the ecosystem services that they provide. And what I contend is that all of these things are necessary, and no one can be used as a comparator between two different ecosystems. So we'll look at the wildlife at risk from land ore mining. We were able to look at the numbers of individual animals at risk. And remember, there are no plants down there. Something like 47 trillion megafauna at risk from land mining, and about 568 megatons of biomass at risk. That's about the same biomass as the human population. Some of the animals that are known to be at risk, this tarsier in Philippines is on a 60-kilometer island where 10 nickel companies are operating, and its forest is rapidly disappearing. It's endemic and endangered. Jaguars in the southeast of the United States, there aren't many, but proposed copper mines are, if constructed, would take away much of the water resources for them and other wildlife in the Southwest, and would also impede their migration back and forth into Mexico. Here's a bird from the Philippines. This is the Philippine Cockatoo, only about 500 left, give or take, threatened by open pit nickel and chromite mines. So the kinds of animals on land we're familiar with, some of them have very strong iconic status and meaning to people, whereas the ones in the bottom are really not known to us, just becoming known. The mining of the four metals that we've talked about takes place to a large extent in megadiverse countries, that is, countries that have the highest species richness of plants and animals on the planet. And so the potential for danger, for extinctions and for harm to populations is extraordinary, especially because land has so many more species than the deep ocean bottom. On the bottom, the populations are more dilute. The animals are smaller. The largest ones, called megafauna down there, are greater than 2 centimeters in size, whereas the standard definition of megafauna on land and in the surface waters and coastal ecosystems is about 45 kilograms or larger. So this is a little confusing for the public to talk about 2 different kinds of megafauna. In any case, myofauna are the little critters that live in between the grains of sediment, quite abundant down there. And then there are corals, sea stars, holothurians, and also there are deep water fishes. These are more poorly known. They've been studied by attraction to bait traps. There needs to be much more understanding of deep sea fishes, both their numbers and their species identifications. But these are the largest creatures found in the CCZ seafloor area. So we'll look at some of the comparisons that we were able to do. First of all, looking at the density of animals on the abyssal seabed versus the land. And here we're talking in terms of numbers of animals per square meter. This is times 10 to the 6th or 10 to the 12th over here. So there are a lot of little animals. Note here that we've been able to look at the minimum and maximum estimates provided by the researchers on whose papers we drew, the same in land. So those are maximum and minimal estimates for the different categories of size categories of fauna. And in general, the numbers on land are much higher. When we go to the next slide, things will look a little bit different. Here, we've scaled up to the number of organisms at risk in order to make 1 billion batteries. So we're using a lot more land. We have to multiply those per square meter values by the number of square kilometers needed to make the 1 billion batteries. And here, what we did was, number one, took an average between the minimum and maximum values in the previous slide, and then multiplied by the area. And what you can see is on the deep sea floor, the number of prokaryotes at risk is higher. Everything else is lower or about the same. The number of myofaunal animals at risk on land and in the sea is about the same. The number of megafauna at risk on land is much higher. The number of protozoans on land is much higher. But these are fairly large numbers, and frankly, just looking at numbers of organisms at risk is not completely satisfactory. We looked at the largest classes of the animals, and here again, we're looking at larger mobile megafauna on land and in the sea, and also amphibians, reptiles, birds, and mammals. And those are at much higher risk on land, where, of course, they are large components of the fauna. These are not found in the deep sea. However, because the mining of nodules entails the construction of ships and also the construction of refineries and processing plants, those land areas provide the vertebrates that are at risk, shown in this box. And the amount of the amount of, at the low left-hand column, the amount of fauna at risk, megafauna at risk from land in the sea is a very small amount, and it's the result of placement of tailings in the ocean in some locations. So on the whole, megafauna are at much higher risk in land than they are in the ocean. We looked also at ecosystem services, and what I am trying to get across is that in order to make a judgment about what area should be preserved and what area might need to be disturbed, you can't just look at numbers of animals, you can't just look at biodiversity, you can't just look at ecosystem services, but you do need to look at all of those in making a judgment. Ecosystem services are a completely anthropogenic way of looking at things. It's the services that ecosystems and species provide to us. And the list you're pretty familiar with, I think, from TEEB and other efforts. It includes provisioning food, water, stuff like that, regulation of climate, air, waste flows, and so forth, providing habitats for species, maintaining genetic diversity, and then a bunch of important cultural and aesthetic services. And in all cases, what we did was try to estimate where there were serious impacts caused by mining on the ecosystem services of land on the left or the deep sea on the right. And for the most part, the interference with ecosystem services is small or low, with the exception of habitat loss, species extinction possibilities. The same is true on land. So those two areas are of concern, whereas land mining interferes with quite a lot of ecosystem service potential. So summing up, we looked at the megafauna organisms at risk earlier, and this is the comparison we found in terms of numbers of individuals. We looked at biomass at risk, and here's the comparison, roughly 10 times as much biomass at risk on land. And the thing that I want to emphasize that's not shown in any of our graphs or calculations is they completely leave out plants. We couldn't include plants because there are no plants in the CCZ, but plants on land are really the driver for biodiversity, for evolution, for mutualism, and for the richness of life and of ecosystem relationships on land. And that just doesn't show up here. And it's something that has to be considered in making the decision that we're talking about today. Now we come to effects on people. And this is really quite telling, looking at fatalities, illness, vulnerable populations, and cultural displacement. Looking at just the number of miners whose lives will be lost if the billion batteries are produced only from land ores, that will be about 1,800 over the next 28 years or whatever until 2047, based on past experience. It may be a little less as mines replace people with machines, but this is the best estimate that we could give. This is only for miners, and this is only for fatalities. It is not considering the illnesses associated with mining, which are substantial. Miners aren't the only people to die as a result of mining on land. There are nearby villages. There once was one here. This is the results of a tailings dam collapse in Brazil in 2015. A huge tidal wave of 55 million cubic meters of toxic sludge from the tailings pond flowed down a 650-mile river to the ocean. It found its way to a leatherback nesting beach and was headed out to the Abrolhos Islands. 19 people died in this. Another tailings dam collapse in 2019 killed 250 people. There are 80 tailings dams in Brazil and 40 of them are unstable. So this is a worldwide phenomenon. The storage of these kinds of toxic wastes in perpetuity is a very difficult proposition. Another issue, as Dinah mentioned, is child engagement in mining, particularly in the artisanal sector in the DRC. About 40,000 children involved in mining. They're not going to school. They're being exposed to toxic cobalt and other chemicals. And companies who source cobalt are very concerned about this and are looking for other ways to source their cobalt. All land mining takes place within a country. It's done by a corporation. There are about 600 international corporations running something like 17,000 mines globally. And the money from all of that stays within the corporation and within the country for the most part. None of it is shared broadly because the ores are not common heritage of mankind. They're owned privately. This is very different than the resources that the International Seabed Authority is managing, which are the common heritage of mankind to be developed for the benefit of all mankind. And the ISA, founded in 1982, is supposed to be able to create the machinery for fair sharing of those royalties with special attention to impacted nations and developing nations and small island developing states. Now, I know there's some controversy about whether people think this can be done well or will be done well. We all hope so if mining actually is undertaken, but that's in the ISA's purview, and we'll see how that works out. One thing that is true all over the world, mining, among other large land displacement or land use changing projects, interferes with indigenous people in serious ways. Their water sources are either co-opted or polluted. The forests are cut down and what they had once gathered and hunted isn't available. There is toxic dust from mines and dried tailings pits that pollutes their soil and they can't grow crops. It's a mess and a constant source of concern in those populations. So we'll compare these kinds of things seen on land and seen in the deep sea. Lives at risk, and here we're just talking about miners, much, much lower with nodules, no child labor, no impacts on indigenous peoples. The CCZ is far enough from any civilizations to avoid that. And the possibility of dedicated flow of funds and royalty requirements to impacted or other nations that need that help. So now let's recap what we found. The first thing to remember is that you can't get metals anywhere, whether it's land or on the sea, without harming non-living resources to some extent, but especially living resources. That is a given. We looked at the overall footprint of mining on land and mining of nodules. And we looked at the results in relation to our 5 bins of analysis, as Dinah presented at the beginning. And the footprint for land mining is much larger in every respect. Of course, we're still interested in learning more about the biodiversity effects of nodule collection, but we're also learning more about the effects of land mining on local biodiversity. But anyway, larger impact on land. And if you look at it in percentages, here we see on the left the percent reduction of impact of nodule collection relative to production of the billion batteries from land resources. And everything is much, much less, even into the 90% less and greater, with one exception, and that is the amount of land use in the ocean. There is 508,000 square kilometers of ocean that will be used to make the billion batteries. And that is a serious matter. One wishes that one didn't have to do it, but the reason underlying the need to look at and perhaps mine nodules from the deep sea is to avoid further climate change. That is on a 10-year schedule. The need to avoid water shortage. We know that in the next 10 years, water demand is going to be 140% of water availability. And so these kinds of advantages that we see on the left in reducing water use, reducing carbon dioxide emissions, reducing the generation of toxins, all of that is really has to be considered. And we think that looking at the problem from a larger perspective than has currently been done, so that we're not looking at just the ocean, not just the land, not just the atmosphere, but the interaction of all of them, and trying to find the best path forward, recognizing that in doing so, some animals will be hurt, plants will be hurt, some land or at least seabed will be hurt, and we need to consider how to proceed, what the recovery times will be, and what humanity should choose at this very, very crucial moment. Now we'll finish with, in the white paper, you can find this diagram that compares the impacts in terms of numbers and percentage change. And we think that this will be of interest, and hope that everyone will be able to enlarge the perspective, and including us, so that we can work together to find the best way forward for the planet as a whole, doing the least damage that we can. There, thanks. So now we're going to welcome Allison back to moderate the question and answer period.
Yeah, thank you so much, Stephen and Dinah, for your insightful presentation. So we have approximately 35 minutes left, and we are going to dive into the Q&A portion of the webinar. So if we aren't able to answer your question live, this is just a reminder that we will be following up with a complete summary of all your questions and answers after the webinar. So our first question is, will any of the results be reviewed by other scientists to ensure robustness and validity? Is there any possibility for some of this to be put into a peer-reviewed journal? And this is an anonymous question.
Dinah, you want to take that? Dinah,
Thanks. I lost
Yeah.
my unmuting control. Okay.
Yeah.
Yeah. So the question is, were the results peer reviewed? Will there be a publication in a journal coming up? How did we ensure robustness? Right. Is that right? Right.
Yeah.
So, and thanks for the questions. And so, with what turned into a 170-page massive undertaking, is not exactly the format that is well suited to a single peer review journal. So there's some steps we took to ensure robustness along the way, and also tell you about some upcoming articles you may be seeing. But so first, we followed, to ensure robustness, we followed standard LCA processes. We used standard databases and tools and procedures that are used in especially the most quantitative parts of the analysis. We also involved many of the top experts that we cite in some of the analyses, both in some methodology review and to help out with some of the analyses. And then we went through a multi-stage review process. We did both internal and external reviews, about maybe a dozen or so reviewers. We sent parts of the paper or the whole paper, depending on the expertise, and we incorporated that feedback. We also got an external auditor. The Yale Sustainability Center co-founder led that effort. And I think some of you actually have seen that and cited it. The forward in our white paper is a summary of that audit result. So that's how we ensured robustness. And then and we also, of course, identified that pieces of this would be small, compact, and relevant to individual journals. And so we've already submitted a peer review journal article on the climate change portions, so the emissions as well as the carbon sequestration. And we also have a biodiversity impacts paper in development right now. I think that's the question.
Yeah, great, thank you. So our second question was asked on Twitter by No Deep Sea Mining. Why does the Deep Green White Paper fail to meet the well-accepted requirements of a cost-benefit analysis? A cost-benefit analysis would identify major social and environmental concerns associated with nodule mining and attempt to quantify impacts as meaningfully as possible. A CBA would seek to estimate the net benefits of proposed deep-sea mining against its net impacts. Dealing with impacts qualitatively is meaningless and self-serving. Without a CBA, the Deep Green White Paper is of little value to public policy and deep-sea mining decision-making.
I'll take it, even though you're the LCA expert, Dinah.
Sorry, take it.
Yeah, the basic problem there is that the resources that are of most interest to people don't have a price on them. And the indirect ways in which prices in such cases are established just aren't satisfactory. I mean, you could ask a gazillion people, how much would you pay to preserve the life of this beautiful sea cucumber? And they might come up with a number, but it's just a very unsatisfactory way to do it. That's the real problem. Some of these things are monetizable, but many aren't. And I don't think that the CBA is actually the appropriate way to look at the problems that are of the most concern to people. They certainly would do a good job on any physical stuff, but the living resources is very, very difficult.
I'll add to that a little bit. So there can be extensions of CBA that attempt to quantify items in the sustainability realm, so including environmental, social, and economic, as we did. And LCA is a tool designed and for academic and policy purposes, for the special cases where you have your environmental concerns are the primary concerns to understand, and that's where it originated. It got expanded into LCSA to include the other two, as it's very suitable when you have a lot of different dimensions of impact that you want to understand: the climate change impact, biodiversity impact, ecotoxicity, all these different dimensions, when it's harder to roll it up into a single number. So when you have multidimensionality as a key issue, and when you have environmental concerns as a driving concern, LCA is an established, accepted tool for understanding the trade-offs. The lack of the net, so we're looking at impacts but not benefits, but because the environmental concern is so great, and in the end you have the same commodity in your hand, we felt it was most appropriate to use that tool that's comparing the impacts in that way.
I should mention also that we did look at the value of human life. That's a tough one, but it is a standard way of looking at how much a company would pay to save one additional human life. And numbers for those all countries have different values, and the value of a human life varies from something like $10 million in the US, Australia, if I remember, and down to several $100,000 or even less in some of the developing countries. And, you know, that's a very unsatisfactory way to look at people, if you ask me. And it demonstrates the difficulty of doing this kind of thing. Not saying it shouldn't be done, it's just hard, and I don't think it would help us very much with the biodiversity issues. But I hope maybe somebody out there is inspired to try, and that would be great.
Yeah, thank you. So our third question is also an anonymous question. Did anything surprise you while executing the study?
It surprised me that Stephen lives on an island.
It surprised me that I'm still alive. But anyway.
I'll go first. I think one thing that constantly surprised me is how people were eager for results and how long it took for us to finalize it. Actually, this paper went through something like 20 iterations already. So it is we care about getting it right and getting the relevant, useful information for a good system level decision. That is a commonality between me and Stephen, and that's partly driven it to take such become a 170-page undertaking. Also, when the first phase for me was building the global warming potential model, and then other things, we expanded the scope of what we wanted to look at. But before we ever got the first result, we're getting all the data, and we have a sense for what the impact we think would be different. But it wasn't, you press the button, you get the first number and you see it, and you're like, okay, is that right? Are you sure? Is it really that much lower? And you have to go through all the validation and make sure you didn't miss something. But that was a bit of a surprise, I would say. And then each time we added, what about these relevant indicators? How do these look? And they kept coming out so drastically lower. That was, for me, the surprise part.
For me, I was impressed with the infrastructure that was available for looking at non-living resources and impacts and energy flow and all of that stuff through EcoVent and other commonly used analytical tools. But there isn't anything like that for living resources. And it's much harder to understand how to do comparisons and evaluations. I should also say the CCZ, while not as everyone used to think it was a flat, featureless plain that was dark and nothing lived there, or not much. And it turns out it is much less featured than land, but it still has lots of variability and lots of creatures living in it. They're small for the most part, loads of nematodes, loads of worms of different species or operational taxonomic units anyway. It's a very different system than on land where there's so much geographical variability and so much floral variability, and all of that drives so much subsequent biodiversity. And every mine is different in different countries in a different setting. And so we had to find ways to try and average results. It would be wonderful to be able to look at each of the however many mines would be involved, but you saw just for manganese how many mines were on that one graph, and most of the companies don't have data on the subjects that we're interested in, certainly with living resources. So I hope that over time the databases and tools for analyzing living resources will come to match those for analyzing non-living resources.
Yeah, thank you. So our fourth question was asked on Twitter. Why is battery technology not mentioned in your white paper? The hunt is on everywhere for better and cleaner metals. This totally undermines the foundation on which this report is built.
Sure, I'll take that. I think, I'm assuming this is in regards to, there's efforts underway by Tesla and many others to find battery chemistries that don't rely on some of these critical metals. So, so the answer to that is sort of twofold. First, what we're looking at is the impact of these four metals that are necessary for the green transition. And I'll combine the two parts into one. Any new technologies that evolve do take time. And so in the market forecasts that we use, and all the metal market experts are looking at these questions and projecting out how much metal is going to be needed. And they're suggesting that with the best information we have right now, they're going to be needed. Now, disruptions can happen. They tend to take 10, 15, 20 years, maybe faster if possible, but to penetrate globally into all of the markets. So the best information we have right now is that these metals and these batteries are relevant to study. But more importantly, we're doing a scenario analysis, creating a clear and consistent set of assumptions against which to compare impacts. And this is a plausible and possible future, but even if the battery technology changes, the green transition still requires the metals, and the question is still relevant. It's just the framing was chosen in that way. So it's a scenario framing, which is important to keep in mind, but it's a likely framing.
Yeah, I'd add to that there are lots of different batteries in research stages, and batteries are used for very different things. Some batteries are good for this process. Some batteries are good for bulk storage at a power station, and some are good for smartphones or other things. They're all different. And so right now, the industry is committed to making electric cars, and the battery of choice is the one that we're using. As you know, there's also research on hydrogen-powered cars, and some have been made. But we've been hearing about it for a long time. How long would it take for hydrogen-powered cars to actually penetrate into the economy? These things happen slowly, and our analysis was based on what the industry is doing now, what demands seem to be now, and it could change in time, but probably for the next 25 years, this battery will be the one to drive the electric fleet.
It's also notable that our assumptions, the 1 billion, are only for passenger cars. So there's obviously going to be potential greater needs beyond that. And also, we modeled, there's a question, I don't know if we'll get to explicitly, but we modeled recycling in place so EV battery has maybe around 10-year lifespan. So in our demand scenario, we assumed every EV battery recycled itself in the future. So we only modeled producing 1 billion EV batteries, not including the replacement when someone buys the new car to replace the one they have to scrap. So we did assume recycling into that. And so in actuality, well, those two assumptions might be relevant to some people.
Great, thank you. So our next question is also from Twitter from No Deep Sea Mining. There are other better ways that we can source what we need, including through recycling and the simple reduction of demand. We can do things better in a post-COVID-19 world, and we need to do things better. What are your views on this?
I'll take that. I think those would all be great. I just don't think we can rely on them. Recycling should be done better than it's being done now. But for metals, on the whole, they're doing what they can. There just aren't the metals in circulation right now to allow recycling to fulfill demand. It's really that simple. Reducing demand, that's a wonderful thing. And it may be that post-COVID, people will reduce demand in some ways. One hopes so, but at the same time, remember, population is steadily increasing, and developing countries are, if things go well, developing middle classes and people who will have increased demand. So those big social forces at play are probably going to result in an increased demand rather than decreased demand. So we'll see how this all plays out. Unfortunately, we will. But I don't think that those other alternatives are really going to solve this problem. And certainly not at the speed at which it needs to be solved, because the transition to a renewable economy has to be done quickly in order to avoid the climate change effects that we know are coming if global temperature exceeds 1.5 degrees centigrade above the Industrial Revolution baseline.
Yeah, thank you. So our next questions were from Twitter. This is a two-part question. Why do you think that deep sea destruction is necessary when there is no evidence that terrestrial minerals are insufficient to meet future mineral demand? And the second part is, why destroy vast areas of the deep ocean when there is no evidence that the minerals are required for a green transition?
Can I
Sure,
take
I
it?
can take.
Oh, okay.
Yeah, go for
go
it.
ahead. Go ahead.
All right, okay. Well, I'll try and then you can correct me. So first part, deep sea destruction is necessary. The first thing I would say is that rather than framing the question, I think the framing of the question is important, and it frames your decision and your understanding of the situation. So rather than framing it of should we or should we not, how do you avoid deep sea harm as the objective? Our objective was the planetary perspective, which is this other question of how do we get all of the battery metals and metals necessary for the green transition with the minimal economic, social, and environmental harm to the people and to the planet. So we're trying to understand what's the harm in these three buckets and figure out if one of them is much smaller than the other. And it turns out it looks like that there's a significant material compression of these environmental and social impacts when you go to the nodules. So the word, is it necessary to do harm, is not how I would frame it. It's a tough question. Of course, we're looking at a system-wide, how you make any big multidisciplinary, multi-dimensional decision, looking at the system of all the impacts and categorizing them as best you can. So that's the first part of the question. And then the rest was about evidence that there's sufficient minerals to meet the green transition. So importantly, there's a difference between metal sitting in the ground and metal that's economic enough for the project pipelines to be created for the industries to mine it and then produce it. And of course, there is enough mineral in the ground theoretically for the green transition, but experts and analysts and metal market industry people who study this intently and project and trying to understand the supply and demand, they're the ones that are saying, look, it's not going to be enough, because they see the project pipeline is not going to be enough. So specifically, in our case, the most problematic being the nickel and cobalt. And some of the issues with nickel being the type of nickel ore needed for that battery grade metal is a type of ore that's in dwindling supply with not a lot of projects in the pipeline, and it's difficult and costly to switch to the other kind. And for cobalt, it's massively scaling up the demand and relying on the DRC, as I mentioned earlier, and the stability risks. And so anyone who asked this question, you look to the fact that Tesla and other companies are trying to find alternatives to the batteries. This is the reason they are, one of the main reasons they're trying, is because of the risks to the nickel and cobalt supply chains. Does that help?
Yes, thank you.
Okay.
So our next question is another two-part question that was asked by No Deep Sea Mining and Deep Sea Conserve. So the first question, why do you not place any value on deep sea species, ecosystems, and related ecosystem services? Your white paper acknowledges that the most significant impacts of nodule mining will be on biodiversity, deep sea species, and ecosystems that are largely yet to be identified and studied. And the second question, Deep Green misses the big picture. The deep ocean is vital to all life on Earth. It helps make our planet healthy. Marine ecosystems provide critical fisheries, coastal protection, food security, and cultural benefits to communities worldwide. How do you plan on protecting it from irreversible harm?
Well, let me take that second part because I still remember that one. You'll have to remind me about the first. But the CCZ is halfway between Hawaii and Mexico. It's at a depth of 4,000 meters to 6,000 meters roughly. It's really quite far from any people, any coastlines. It is not activities down there. There are no fisheries, certainly on the bottom. The fisheries, it is not a productive area. The eutrophic zone just simply isn't. Food supply dropping down is very low. We do not think that collecting nodules down there is going to hurt any coastal fisheries or any other resource flows. Certainly not significantly. As for the ecosystem services, we did analyze them, and we do not think that the flows of services are going to be materially affected. They either aren't flowing because they're not connected to people very closely, and the ones that are, for example, the biodiversity, genetic resources, and so forth, we think that there will be harm. Much will recover, more or less at about the same rate as forests recover. Some will take much longer, that is the obligate nodule residence, and of course, any production of new nodules. But we think that the impact down there is not going to interfere with the services that were mentioned in part 2 of that question.
I would also just add to that that we clearly placed value on it, and unfortunately there's so many more categories of impacts to cover than just biodiversity. But if you remember the spider chart with the 2 areas of the nodules and the landors, and you saw that biodiversity is the one where it comes up and it almost touches, I mean, if we just went quantitatively by the number of organisms, it would not have come close. Like, we're acknowledging and putting in the uncertainty of what cannot be known yet to adjust and to come up with that final number where our overall assessment on that specific indicator is that it's difficult to compare them because of the uncertainty.
Yeah, I think
But in many cases, there is certainty.
this is one of the most important questions that's asked because it mentions value. And here it's not talking, I think, about financial value. It's talking about value, the existence value of organisms, and how we, as humans, value the organisms and the system itself. And I mean, I place a very high value on organisms. I'm a gardener and I rescue worms. I try not to kill anything. I don't like doing that. So it's with great reluctance that I would want to be part of any system that killed things. Well, the fact is, I also drive an automobile, and it requires metals. Those metals had to come from somewhere. They came from land mines. And in the course of that action, I was responsible for my share of the destruction of whatever forest and whatever animals and plants and everything else that was in there. So it's really trying to do the minimum amount of harm. And in the end, I think we as humans are going to be, if we're not already, forced into positions where we assign different values to different organisms. We really are going to have to choose either to not do the green transition, in which case we probably all roast, or to somehow magically and immediately find some solution that doesn't require the metals that we've been talking about. And that's a good wish, but I don't think it's likely to happen. Or we have to get the metals that are required from somewhere. And if we say, well, let's just leave the deep sea alone, it's lovely and it doesn't deserve harm, then we're participating in a great deal of damage on land, species extinctions for sure, species extinctions of things that personally I think would matter more to people than extinctions of a nematode that maybe hasn't even been named, or a worm, or possibly a sea cucumber. I would prefer, if I had to choose, saving snow leopards or orangutans or Philippine tarsiers, or any of a number of things that have more iconic and spiritual and aesthetic importance and meaning to me, and I think to many people, than an invertebrate on the bottom of the ocean. Hopefully, you don't have to get into extinction there, but you do end up with a period of damaged population, which would require a lot of time for recovery. And if ocean mining did take place, I think we owe it to the habitat to give it all the time that it needs to, which is going to way outlast us, to recover. It will recover. It will take time. We should make sure that nothing else happens down there, hazardous waste dumping or whatever, that would impede recovery. But I would see it as a necessary sacrifice to get through the very narrow window we have to save the planet from excessive overheating and get into a more renewable age.
Yeah.
It would be with regret, but that's how I feel about it.
Yeah. Well, thank you for your detailed answer. So our next question is a multiple question. One of them was asked during our May 6th webinar, and the other two were asked on Twitter. So our first question, how long does it take the CCZ ocean bottom habitat to recover after nodules have been collected? And what do we know about the recovery for land versus deep sea? And the second question, world-renowned deep sea ecologists such as Vandover et al. 2017 have asserted that remediation and offsetting are not viable options for deep sea mining. What is your response to this? And another similar question, your report does not include the best available science indicating that the impacts of nodule mining are likely to be severe and long-lasting, effectively irreversible in human timescales. Why not?
Got it, Stephen. I'll take this.
Which one? Well, you take one and I'll
No, it's
do
yours.
Go ahead.
I was joking. I think this is your expertise.
Okay. All right. Well, let's start with the Vandover. She's right. That's true. There will be long-lasting disturbance, and there is no apples-to-apples offset. The only thing you can do is create non-mining protected zones and also protect other nodule areas from any mining or collection. We don't like to call it mining simply because you're not digging around. You are blowing sediment away from the nodules and then picking them up. The top 10 centimeters of sediment at most is disturbed. But in any case, it will be disturbed over a large area. Some recovery takes place relatively quickly, starting soon and taking decades. Some of the holothurians, sea cucumbers, sea serpents, serpent stars, they can come back pretty quickly. Some other things take a longer time. The bacteria, a recent study suggests that they begin recovering soon, but probably it would be after 50 years that you would begin to approach full recovery of the bacterial populations. The obligate fauna is going to take obligate nodule fauna a long time. Probably 15% of the nodules won't be harvested, and those that remain on top of the sediment will be able to be colonized. And so what we compare this to is recent work in the Amazonian Atlantic forest and rainforest show that after about 65 years after cutting, the secondary forest regained about 40% of its carbon sequestration services. And it takes on the order of 100 years for the shade species to come back in, and about 4,000 years to get back to its pre-impact state. So with the exception of the nodule fauna and the nodules, things down there will probably recover at about the rate of a rainforest, which is a long time. Some of it in human terms and some of it much longer.
Great.
There were other parts to that. I don't remember what they were.
No, I think your answer covered all of the questions, so thank you. We will be following up with a complete summary of all the questions and answers, so if we missed anything, we'll be more thorough in that summary. So we are at time, but I do want to just finish our questions, so if you have to sign off, that's okay, but feel free to keep watching if you have time. So our next question, as more research is conducted, it is becoming apparent that the deep sea, midwater, and surface ocean ecosystems are interconnected by currents and upwellings, cycling energy and nutrients between them, and by the movement of fish and other deep diving species. How will this be addressed?
I can take a shot at that again. Actually, most of the nutrient and energy movement is through either sinking of phytodetritus and dead organisms from the overlying water column, or from movement of organisms, either diurnal vertical migration in the mesopelagic zone particularly, but some migrations that are deeper, and then the feeding migrations of whales, elephant seals, maybe leatherback turtles, and other things that feed in deeper water, and then transport nutrients vertically or horizontally through their excretions. So that's pretty important in the overall functioning of the zone. We're not aware of large horizontal currents at this point that are transporting things from the CCZ out or in. So it's largely the animals that are doing the most immediate trophic cycling. Well, those things are being investigated. Any contractor who has an exploratory lease has to do a very thorough environmental impact assessment, and that's where all of those things are looked at. The marine mammals, and both visually and by sound, and then counting and using ROVs and identifying. So there's much to be learned for sure about the overlying water column. We're not worried about the surface 1,000 meters because the discharge pipe would be below that. But engineers and biologists are working together to try and find out what depth the discharge should be at to minimize harm to the water column and to the functions that we've just mentioned.
Great, thank you. So our next question was asked live during this presentation by an anonymous participant. What do you predict the greatest opportunity for job growth related to the sourcing of critical energy transition minerals?
So I can take that. I'm assuming that the question is regarding if nodules are used. Is that your interpretation?
Yes, I think
so. I can answer that version. So I showed the charts with the jobs per country, assuming nodules were not used. The difference for nodules is in part, since it's an international resource, the job opportunities would be a sort of international and not tied to the location of where the resource is found. And the opportunity, since rather than the processing aspects are fairly similar, so those jobs wouldn't really be any different than what you would expect from the landor side. The difference may be in the collection part. So you're going to see with nodules, ship operators, large ships that require personnel to operate the ship, but also more technical and more high-tech command and control type roles, because you'll have people operating remotely the systems that are 4 kilometers below them, collecting the nodules. You also have people employed to do the transfer or assist the machines in the transfer of the nodules onto the transport ships themselves. And then you'll also employ people in the shipping fleet to, rather than the current transport, trucking and other types of transport from mines to the processing plant. Here you'll have the shipping fleet employment numbers. So I would say, and additionally, you have the engineering and maintenance and construction of the actual ships and collector systems. So those are the buckets of jobs I would be thinking about.
Okay, thank you.
Hmm.
So our next question was asked during our May 6th webinar. Based on everything you learned in this study, how do you feel about the trade-off of land or nodules?
Do you want to take it first?
Okay. Well, I was struck by the results and by how decisive the advantages appeared to be for sourcing the battery metals from nodules. And so at this point, that appears to be an advantage that has to be seriously considered. Dinah and I are just analysts asked to do these comparisons and see what we found. We don't have to make the decisions about what to do and whether to mine. That is up to the International Seabed Authority. And so it's their obligation to take all of the information that we provide and that the other organizations provide and try and come to the very best decision they can that's the best for the world, because that's their purview. So as I say, I regret harm to any animal, but I see harm in both places. And what I'm feel is that the overall good to the planet and to people and to wildlife has to be the basis for the decision. And if the CCZ is to be mined, I just hope it's done as carefully as it can be and with as much thought, as much protection, both in preserved areas such as the APEIs and set-asides by contractors, and collecting schemes that produce the most possible sites for recolonization. And if there's any kind of active remediation that could be done, and I think that would have to be limited, but if there were some strategic things that could be done that could speed recovery, that I think that would be well worth considering. I think life is resilient, and there will be a spread of larvae and organisms from protected areas that will slowly increase the populations and the functions of the deep sea area too, very gradually toward its original state. That will take a very long time, but I think it could happen. So, it's somewhat regretfully that I say this, but it looks to me as if the metallic nodules may provide the best way forward toward the green transition that we've got to get to quickly.
Great.
Yeah, I agree with all that. And I would say that it's a tough decision. It's always difficult to disrupt something new that you haven't disrupted before in this way. And I understand that reservation a lot. I also then think about the flip side. Can I imagine anybody looking at the data that I've seen, that Stephen's seen, and the analysis that we've done, and concluding from that, you know what, I think the land ores is much better for the planet. The land ores as a resource for these metals, taking all the impacts into account, it seems like a really hard sell. It seems to me that the overwhelming compelling case is that even with a few things we don't yet know, but we are trying ongoing environmental impact studies that are required by the ISA to learn more about those things. I don't see how the data indicates that it's better to continue using land ores rather than trying to lessen the impacts and use the nodules instead.
Yeah, thank you. So our final question, this was asked by email by Con Nugent, a senior fellow at the Ocean Foundation in Washington, D.C. Are there plans afoot for the production of a comparable study in which the marine mining under discussion would be removal of cobalt-rich crusts?
I think there are, of course, environmental impact statements required for any ocean mining, but I'm not aware of any other studies that compare the land effects and the ocean effects of, for a deep sea mining project. And it does seem to me that for any mining project, this is a very good approach. And so I'd encourage similar studies for seamounts and for hydrothermal vents or any other source. I think it's a good discipline. It's important. You learn a lot, and it can inform decisions. And we don't know how those would come out. And this isn't by any means to be interpreted as encouragement for such activities, such mining. But I do think whenever it's contemplated, looking at the project in the planetary context is really important and a way that we need to conduct ourselves.
Yeah, thank you. So thank you so much, Steve and Dinah, for your insightful answers. I'm now going to welcome back Dr. Greg Stone to close us out.
Hi, everybody. I hope you've learned something. Hi, everybody. I hope you've learned something and enjoyed this seminar. I'd like to just leave you with one thought, and that is to dial it back to the bigger picture for a moment here and remember that hominids, our line of creatures, started about 6 million years ago, which led to Homo sapiens. Now, during that whole time, we've had icy poles. And those poles, those icy poles, are what make the ocean what we see it today. During the Jurassic, the period in which a lot of the fossil fuels that we're burning now were laid down, we had Bahama-like weather everywhere. And the oceans were like a mill pond. They didn't circulate, and they were stagnant. And the real problem right now is we are changing, warming so fast. We're actually warming 4,000 to 5,000 times faster than when the original Jurassic arrived, that we really have to put the brakes on. And it's not just this solution path that's been laid out today. We need many other solution paths. So I just want to tell you, I've been worried about it my whole life, my whole career. I'm very, very concerned about it now as I see the models, particularly for the icy poles. We're always exceeding the models. The ice is melting, and when white ice, which reflects light and heat back into space, goes away, it's replaced by dark water or land, which absorbs more heat. So that's the runaway effect. So I'll leave you with that thought and the planetary perspective that our wonderful presenters have given us. And I thank you for your attention today, and I look forward to the continuing dialogue with you and others. Thank you very much.
Thanks, everyone.
Thanks, and thanks for those great questions that you asked.
Yeah.
Thanks everyone for joining.